All right, so the last video did part C the hard way. Let's do it the easy way. So part C. Okay, now I want you to kind of look at this. You don't have to redraw this. I'm gonna redraw it to kind of explain, give you a sense of what's going on. We're looking at this 1.5 m, and it's gonna travel on this rough surface, a distance of d, all right? And it's gonna come to a stop. So velocity is gonna equal 0 at the end. Okay, and its speed to start off with is 2v naught. I got that from up here. So we're looking for the coefficient of friction, of kinetic friction. That's when it's moving. So that obviously stops when it stops. First, I just do want to write the equation for that. Force of friction is the coefficient of friction, how rough a surface is, times the normal force, how much the surface is pushing back up on the object. Let's rearrange that for coefficient of friction. And if you notice, these are both force. They'll be measured in newtons, so this thing, as you recall, has no units. Also, I suggest drawing the free body diagram. You don't have to. It usually helps, though. Weight, this is normal force. That's your force of friction. So if you notice here, your weight and your normal force balance each other out because it's only accelerating in this direction. And the acceleration is backwards because, think about it, it's slowing it down. It's kind of like you're pushing something to stop it, but instead of you pushing it, it's the rough surface pushing it. So anyway, I would put by, and I should have put this one in the other one, Newton's second law. They're picky about this now on the newer test. By Newton's second law, the magnitude of your normal force is equal to the magnitude of your weight. Also, I want to point out one other thing. This is what I messed up in the last one. Your weight equals 1.5 mg. Keep that in mind. Let's see. So basically, let's look at this. There is kinetic energy right here. You have kinetic energy to start off with. I'll do that in orange. So your initial kinetic energy to start off with, if you remember, kinetic energy equals mass speed squared over 2. Initial kinetic energy is going to be your mass, which is 1.5 m. Okay, times your speed, which is 2. Well, it's your speed squared, so let me go and square that. I'll go ahead and do this. 2v naught squared over, the whole thing on this would be over 2. So let me go ahead. K equals 1.5 m times 4v naught squared, just distributing this over 2. That would be, see that 4, that would go to 2, so you're left with 2 times 1.5 is 3 mv naught squared. So that's your kinetic energy to start off with. So what's your kinetic energy when you end? Well, there is no kinetic energy because there's no speed. So if you notice, you have a change in kinetic energy. Now, if you recall, when do you change your energy? When you do a lot of, well, work. So the change in kinetic energy is going to be equal to work. And work, if you recall, I'll write it up here, is just force dot displacement, and that means cosine theta. You don't have to worry about that right now because it's just going straight. So let's go ahead and look at this. Your change in kinetic energy would be your final 0 minus 3 mv naught squared. So I'm just going to write that. I'm not going to worry about the negative sign. That just tells you if work's done on or by. Okay. So, and then your work would be the force, what force is doing work on this? It's going to be your force of friction, okay, times, not worried about the dot product, how far did it go? D. So what I'm going to do here is solve this for the force of friction, so I can plug it in up here. So that's pretty easy. I just divide it by the D. Okay, so your force of friction is 3 mv naught squared over D. And we already know the normal force up here. It's just 1.5 mg. So what I'm going to do is go 3 mv naught squared over D. And that's going to be divided by normal force, which is 1.5 mg. The 3 and the 1.5 cancel out to 2. Ooh, ran out of room. So therefore, mu, your coefficient of kinetic friction, will be 2m. Oh, my m's cancel out too. Will be 2 v naught squared. Whoops, that's 2v naught squared over dg. Okay, let's check that. Okay, so here is the, in theory, here is the key. Okay, so let's take a look at this. It says, alternate solution. For any indication that work done on the block slide is equal to its initial kinetic energy. Well, yeah, we got that. See right here? This FD, we have that, is equal to 1/2 mv naught squared. Yeah, we have that. I just plugged the numbers in right here. And also, this should work since I indicated up here that this is 0 and that this is 3 mv naught squared. So, either which way, that works. So I'm going to give myself 1 point for this. Okay, for a correct expression of the work done on the block. So the work done on the block was force of friction times d. Yes, that's 1 point. We have a correct expression of the initial kinetic energy of the block. All right, so that would be, where is it? Like right here. See, look, this is your force of friction acting on the block. They kind of broke this down more. See how I had solved for force of friction over here? And then basically all of this work goes into with this, goes in with this, and that creates this. See, people do problems a different way. They can't do every single way, but if you look, I hit all of the major points on this. So that is also worth a point. And then the correct answer, 2v naught over dg, right here, is also worth a point. So this one's worth 4 points. The video is longer on this because I spent a little bit more time explaining, but this process should be a lot quicker. That being said, use whichever one works best for you, even if it is kinematics, but there's a lot less chance to make a mistake here.